Crystal lattice and unit cells. Crystalline solids have an orderly arrangement of their constituent particles in three dimensions. The positions of these particles in a crystal lattice to one another are usually shown by the points. An arrangement of an infinite set of this point is called a crystal lattice. Thus, a crystal lattice is a regular arrangement of the constituent atoms, ions, or molecules in three-dimensional space. Sometimes a crystal lattice, also called a space lattice or simply a lattice. There are only 14 possible three-dimensional lattices and are called Bravais lattices. Bravais lattices, okay. After Auguste Bravais, a French mathematician who first discovered this. Now let's look at the characteristics of a crystal lattice. Each point in a lattice is called a lattice point or lattice site. Each point in a crystal lattice represents one constituent particle, which may be an atom, a molecule, or an ion. Lattice points are joined by straight lines to bring out the geometry of the lattice. A crystal lattice can be subdivided into several parts known as unit cells. Thus, a unit cell can be defined as the smallest portion of a crystal lattice which, when repeated in different directions, generates the entire lattice. A unit cell represents the shape of the entire crystal. A crystal may consist of an infinite number of unit cells. A unit cell is characterized by distances AB and C along three edges and angles alpha, beta and gamma between pairs of edges. Alpha is the angle between edges B and C. Beta is the angle between edges C and E. And gamma is the angle between edges A and B. As shown here, unit cells can be broadly classified into two categories: primitive unit cells and centered unit cells. Unit cells in which all the constituent particles such as atoms, ions or molecules are present only at the corners are called primitive unit cells. And unit cells in which one or more constituent particles are present at the position other than its corners in addition to those at the corner, it is called a centered unit cell. Based on the position of the centered constituent particles, centered unit cells are categorized into three types: body-centered unit cell. Three types: body-centered unit cell, face-centered unit cell and end-centered unit cell. A body-centered unit cell has the constituent particles at all its corners as well as one particle in the center. A face-centered unit cell has a constituent particle at all its corners as well as at the center of each face. An end-centered unit cell has one constituent particle at the center of any two opposite faces besides the ones present at its corner. You know that a three-dimensional crystal lattice is generated by the translation of lattice parameters A, B and C. Based on the lattice parameters, we had 7 popular crystal systems, mainly cubic, tetragonal, orthorhombic, hexagonal, rhombohedral, monoclinic and triclinic. Let's discuss each in detail. In a cubic crystal system, all the three axes are of equal length and are at right angles to each other. The possible lattices are primitive, body-centered and face-centered. Sodium chloride, zinc blende and copper are well-known examples of this type. In a tetragonal crystal system, the three axes are at right angles to each other, but only two are equal. The possible lattices are primitive and body-centered. Calcium sulfate and titanium dioxide are the examples of this type of crystal structure. In orthorhombic crystal system, the three axes are unequal, but all the axes are at right angle to each other. The possible structures are primitive, body-centered, face-centered, and end-centered. Rhombic, sorry, Rhombic sulfur, potassium nitrate and barium sulfate are examples of this type. In a hexagonal crystal system, two edges are of equal length and two angles are of 90 degree and one angle is of 120 degree. The only possible lattice is primitive. For example, graphite and zinc oxide. In a rhombohedral or trigonal crystal system, the three axes are of equal length and inclined at the same angle, but the angle is not equal to 90 degree. The only possible lattice is primitive. Calcium carbonate and mercuric sulfide are examples. In a monoclinic crystal system, the three axes are of unequal length and only two angles are of 90 degree. The possible lattices are primitive and end-centered. For example, monoclinic sulfur and decahydrate sodium sulfate. In a triclinic crystal system, the three axes are of unequal length and all angles are different and none is equal to 90 degree. The only possible lattice is primitive and potassium dichromate, boric acid and copper sulfate pentahydrate are some examples. Crystal lattice is made of an infinite number of unit cells, and every unit lattice site is occupied by a constituent particle that may be an atom, an ion, or a molecule. Now let's examine what portion of each particle belongs to a particular unit cell. Consider three types of cubic unit cells. For the sake of simplicity, assume that the constituent particle is an atom. Let's start with a simple or primitive cubic lattice. A simple cubic lattice consists of 8 atoms at the 8 corners of a cube. In the open structure shown here, the distance between the atoms are greatly exerted. In reality, the atoms are packed much more closely together, as shown in the space filling model here. The space filling model shows that the atoms touch along the edges of the cell. By considering the portion of the atoms inside the cell boundary, we can generate a unit cell of a simple cubic lattice. From this, it is evident that each atom at the corners contributes 1/8 of its original volume to each unit cell. There are 8 atoms at the 8 corners. Thus, the number of atoms in each unit cell is equal to 8 corners. Atoms into 1/8 of an atom per unit cell, which is equal to 1. A body-centered unit cell contains 8 corner atoms, just like in a simple cubic unit cell. And there is one more atom at its body center. As a result, the atoms at the corners no longer touch along the edges of the cell in the space filling model. The unit cell for body center cubic cell is shown here. It is clear that the 8 atoms at the corners contribute 1/8 of their actual volume each. In addition, one atom lies completely inside the cell. Therefore, the number of atoms at the corners per unit cell is equal to 8 corner atoms into 1/8 of an atom per unit cell, which is equal to 1. There is one atom at the center of the cube. Thus, the total number of atoms in a body-centered cubic unit cell is 2. The face-centered cubic lattice consists of 8 corners atoms, just like in the simple and body-centered cubic lattice. However, it also contains 6 more atoms at the 6 faces of the cube cell. The atoms touch along the diagonals and each touches 4 corner atoms. A unit cell of a face-centered cubic cell is shown here. It is clear that the atoms at the corners contribute 1/8 of their original volume each. In addition, there are 6 atoms at the 6 faces, which contribute half of their original volume each. The number of atoms at the corners per unit cell is equal to 8 corner atoms into 1/8 of an atom per unit cell, which is equal to 1. The number of atoms present at the faces per unit cell is equal to 6 atoms at the faces into half an atom per unit cell, which is equal to 3. Thus, the total number of atoms per face-centered cubic unit cell is 4.